In this video, we are going to talk about L'Hopital's rule. First, we'll look at the indeterminate form and how it relates to the Cauchy mean value theorem, and then we'll look at limits at infinity and L'Hopital's rule. The indeterminate form comes when you have the limit of a quotient, such as the limit as x approaches c, f of x divided by g of x, where limit as x approaches c of f of x equals 0, and the limit as x approaches c of g of x is equal to 0. What you have is something that looks like limit as x approaches c of 0 over 0, and this is the indeterminate form. And we call it indeterminate because sometimes the limit does not exist. Other times the limit does exist. It's indeterminate because once you have this form, you really know nothing about the limit until you have to look at the particular f of x and g of x. But this by itself tells you nothing. An example of an indeterminate form is f of x equals x times a constant k, and g of x is equal to x. So the limit as x approaches 0 of f of x over g of x is xk over x, which is equal to k. So depending on which k you have in your f of x, so f of x is equal to 3x, you're going to have a different limit than when f of x is equal to 4x. And in this case, the limit does exist, which is not always the case with indeterminate forms, as we mentioned before. Sometimes you would take this quotient and you would do some sort of simplification or cancellation, in which case you can work with the resulting limit. L'Hopital is a more general way of dealing with indeterminate forms and often an easier calculation to do. To help us get to L'Hopital, we're going to start with the Cauchy mean value theorem. Let f and g be functions that are continuous on the closed interval ab and differentiable on the open interval ab. Then there exists at least one point c in the interval such that fb minus fa times g prime of c is equal to gb minus ga times f prime of c. And I have rewritten this Cauchy mean value theorem into this form. Just for whatever reason, it's easier for me to look at and to remember this form here. The Cauchy mean value theorem, which I've underlined in blue, the formula here, and also rewritten in this form here, is a generalization of the mean value theorem that we covered in the last video. So I've underlined that in green, as well as I put the theorem in the drawing here for your reference. To see that the Cauchy mean value theorem is a general form of the mean value theorem, we're going to take the Cauchy mean value theorem and set our function g. We're going to let it equal to g of x equal to x. So the mean value theorem is a specific case of the Cauchy mean value theorem when we let g of x equal to x. Now then g of b will equal to b, g of a is equal to a. G prime, or the derivative of g, will equal to 1. In particular, g prime of c is equal to 1. So now our Cauchy mean value theorem, which I rewrote here, will give us f of b minus f of a. Now we plug in, for g of b we plug in b, and for g of a we plug in a, so we have b minus a, equals f of c over 1. And this is exactly the mean value theorem. And now we are ready to prove the Cauchy mean value theorem. We are going to start by letting h of x equal to this constant over here. And I know it looks like a big term, but it's just a constant, times g of x minus g of a minus f of x minus f of a. And since h is a kind of a linear combination of f and g, which are both continuous on the closed interval and differentiable on the open interval, then h is also continuous on the closed interval and differentiable on the open interval. Now we will consider h of a. So when I plug in a here, I have this constant times g of a minus g of a, so this goes to 0. And then I have f of a minus f of a, so this also goes to 0. So in this case, h of a is equal to 0. Now let's plug in h of b. So I have my f of b minus f of a, g of b minus g of a, my constant. Then I have g of b minus g of a minus And again, plugging in b for x, f of b minus f of a. So these two cancel out, and I get f of b minus f of a minus f of b minus f of a. So again, I have h of b equal to 0. So both endpoints of my function h is equal to 0. By Rolle's theorem, that means there exists some c in AB such that h prime of c is equal to 0. That is, h prime of x over here, this is a constant, it stays. My g prime of x, that needs to become g prime of x. This is a constant, so also this constant times a constant, this is going to drop out. It's going to be 0. The derivative of a constant is 0. I have my f of x. To take the derivative, I'm just going to have f prime of x, and f of a is a constant, so that's also going to drop out. And this derivative, h prime of c, is going to equal to 0 for some x equal to c. So next I'm going to plug in my c, and I will get my constant here, g prime of c minus f prime of c is equal to 0, and I can rearrange my terms until I get this form or this form here, whichever you prefer. Now we are ready for L'Hopital's rule for the indeterminate form. So let f and g be continuous on the closed interval AB and differentiable on the open interval AB. Suppose that c is in the interval AB and f of c equals g of c, which is equal to 0. So we have this indeterminate form as x approaches c. Suppose also that g prime of x is not equal to 0 for x in U, where U is the intersection of AB and some deleted neighborhood of C. If the limit as x approaches C of f prime of x over g prime of x is equal to L, where L is a real number, then the limit as x approaches C of f of x over g of x, that indeterminate form over here, will also equal to L. And now we are ready to prove L'Hopital's rule. It's actually a very quick proof. When I look at the limit as x approaches c of f of x over g of x, you can see I get the indeterminate form. So now I'm going to consider f of x over g of x. I'm going to subtract f of c from the top and g of c from the bottom, and I can do that since f of c and g of c are both equal to 0. My next step will be to divide the numerator and the denominator both by x minus c. Now when I look again at the limit as x approaches c, I had the limit of f of x minus f of c over x minus c, g of x minus g of c over x minus c. This here in the limit is f prime of c, and this here in the limit is g prime of c. So I have the limit as x approaches c of f of x g of x is equal to f prime of c, g prime of c. I have this alternate proof, which is much more complicated, and I won't go through it, but I have it here for your reference. Here we have our first example. Let f of x equal 2x squared minus 3x plus 1 and g of x equal x minus 1. Then you can verify that f of 1 and g of 1 are both equal to 0. We want to find the limit as x approaches 1 of f of x divided by g of x. The first problem is very straightforward. You can see we have the indeterminate form. As the limit approaches 1, we have 0 over 0. But f and g are both continuous on the interval 0 to 1 and differentiable on the open interval, and g prime of x, which is equal to 1, is not equal to 0. So it satisfies the condition of L'Hopital's rule. So we can take f prime of x, g prime of x, and the limit as x approaches 1 of our original quotient, 2x squared minus 3x plus 1 over x minus 1, is equal to the limit of f prime of x over g prime of x, and as x approaches 1, that will equal to 1. Our next example is f of x is equal to e raised to the 2x minus 1, and g of x is equal to x. You can verify that f of 0 and g of 0 are equal to 0. So you want to find the limit as x approaches 0 of f of x divided by g of x. Here we have the indeterminate form, but we do have that f and g are both continuous on 0, 1, and they're differentiable on the open interval. We also see that g prime of x is not equal to 0, so it satisfies the conditions of L'Hopital, and we can take the derivative of f and g, so we have 2 e to the 2x over 1. The limit as x approaches 0 is equal to 2, and therefore that would be the limit of f of x over g of x. Now we can consider trigonometric, exponential, and logarithmic functions with indeterminate forms, we can evaluate these limits. We wouldn't normally be able to handle them just by factoring. So for example, let's find the limit as x approaches 0 of 1 minus cosine x divided by x squared. We can verify that our f of x over g of x as x approaches 0 is our indeterminate form 0 over 0, but we can also see that these two functions are continuous on the interval 0 to 1 and differentiable on the open interval, and g of x is not equal to 0 except at x equals 0, or g prime of x, which is 2x, is only equal to 0 at x equals 0, so it is not equal to x in the deleted neighborhood, which means we can apply L'Hopital's rule. So I can take the derivative, so the limit of 1 minus cosine of x over x squared is equal to the limit taking the derivative of the top, I will get sine of x, and the derivative of the bottom, I get 2x. And you can see when I plug in x equals 0, I still get an indeterminate form. But both of these functions are also continuous and differentiable, and not g prime of x here is not equal to 0 at all because it's just equal to 2. So I can again apply L'Hopital, and I have the derivative cosine of x over 2, and as x approaches 0, that will give me 1/2. The two things to note is I verified that L'Hopital's rule was applicable to this first quotient, so I applied L'Hopital's rule, and I still found an indeterminate form. So I looked at the new f of x and g of x, this quotient, determined that L'Hopital's rule still applied, and so I applied L'Hopital's rule one more time. The second thing, as you noted here, when we looked at g of x, the derivative of g of x, we saw that g prime of 0 is equal to 0, but that's okay because to follow L'Hopital's rule, it's not that the g prime of x is not equal to 0 anywhere, it's that it's not equal to 0 in the deleted neighborhood of C, so it can still equal 0 at our point C. As we look at L'Hopital's rule for limits at infinity, we need to review two definitions. The first is the limit as x approaches infinity, f of x is equal to L. Provided that each epsilon greater than 0, there exists a real number n greater than a is the beginning of our domain, such that x greater than n implies f of x minus L is less than epsilon. In other words, as x approaches infinity, we reach this limit L. Our next definition, f itself tends to infinity as x approaches infinity. So we write limit as x approaches infinity of f of x is equal to infinity. Provided any real number a, there exists a number n that is greater than a. So no matter how big of an a you give me, I can always find a number n that's greater than a. So that will be the definition of f itself tending to infinity as x goes to infinity. So L'Hopital's rule at infinity, let f and g be differentiable on the interval a to infinity. Suppose that the limit as x approaches infinity of f of x equals the limit as x approaches infinity of g of x is equal to infinity, and that g prime of x is not equal to 0 for all x. Then, if the limit as x approaches infinity of f prime of x over g prime of x is equal to L, then the limit of f of x over g of x is also equal to L. Very analogous to the original indeterminate form of L'Hopital's rule. I will not prove, but I'll do some examples, and the first one is the limit as x approaches infinity of natural log of x over x. The limit of natural log of x over x, if we plug in infinity, natural log of x gets bigger as x gets bigger, and x of course gets bigger as x gets bigger. So this is our infinite form. So we will take the derivative of the top, which is 1 over x, the derivative of the bottom, which is just 1. So we have the limit as x approaches infinity of 1 over x, which will be, the limit will equal to 0. A similar but different example, the limit as x approaches 0 from the positive side of x times minus natural log of x. When I plug in 0 into my x and my natural log of x, I get 0 and infinity. So this form is indeterminate. But of course, my problem is this is a function times a function, not the quotient of two functions, which my L'Hopital's rule is expecting over here. But what I can do is I can convert my x to be 1 over 1 over x. X equals 1 over 1 over x. So that way I can have my form of f of x over g of x and use L'Hopital. And now I can take the derivative of the top, the derivative of the bottom, do some algebraic simplification, and my limit is equal to 0. So this is a good example of when you have a product that's kind of indeterminate, that you can convert one of these functions into a denominator. For our last example, we'll evaluate the limit as x approaches 0 from the positive side of x raised to the x, where x is greater than 0. We will start by letting y equal x to the x. So we can now consider natural log of y, which is equal to, we can bring down one of the x's, x natural log of x. And we note that natural log of y approaches 0 as x approaches 0 from the positive. So now we can consider e to the x, which is continuous, and we can look at y, which is e to the natural log of y. And now we noted that natural log of y approaches 0 as x approaches 0 from the positive side. So this is approaching e to the 0, which is equal to 1 as x approaches 0 from the positive side, which means our limit is equal to 1. For this next example, I have 4 limits to evaluate. The first problem, so we have f of x is equal to sine of x, and g of x is equal to x to the 1/2. And you can see when we plug in x equals 0 that we're going to have the indeterminate form. We can also verify L'Hopital's conditions are satisfied, that is, that f and g are both continuous on the interval 0 to 1 and differentiable on the open interval. And then we also have that g prime of x is not equal to 0 except at x equals 0. So then we can set the limit of sine of x over square root of x equal to the limit of cosine x 1/2 1 over square root of x. So that's equal to the limit, just algebraically, 2 square root of x cosine x, plugging in 0 for x, we're going to get 0. So here is the limit. For problem number 2, we can see f of x is equal to sine x minus x, g of x is equal to x cubed, and when you plug in the limit x equals 0, you see that you will get the indeterminate form 0 over 0. You can also see f and g are continuous on the interval -1 to 1 and differentiable on the open interval. G prime of x is equal to 3x squared, which is not equal to 0 except at x equals 0, so that's fine. So we can use L'Hopital's rule, and we get limit as x approaches 0 of sine x minus x over x cubed is equal to, plugging in the derivative, cosine x minus 1 over 3x squared. Now when we plug in the 0, you see we get the indeterminate form again. And I didn't write this out, but you should also know that cosine x minus 1 and 3x squared are both continuous on the interval, differentiable on the open interval, and g prime of x is not equal to 0 except at x equals to 0. So we can apply L'Hopital's rule here, and we have the derivative is minus sine x over 6x. And then when we plug in the x equals 0, you can see we again get the indeterminate form, and again we can see that the functions f of x and g of x are continuous and differentiable. G prime of x is not equal to 0 except x equals 0, so we can apply L'Hopital's rule once again, and we get minus cosine of x over 6. When we plug in 0 this time, we finally get -1/6. And again, we applied L'Hopital's rule 1, 2, 3 times, and I did go through each time to verify that the conditions of L'Hopital's rule were satisfied and it was appropriate to apply L'Hopital's rule. But I did not write down each of the notes that each of these were continuous and differentiable and g prime of x is not equal to 0, but you would want to do that. For the next problem, we have f of x equals natural log of x and g of x equals x minus 1. They are continuous on the interval 1/2 to 3/2. I had to change my interval so it would be around 1, and I just chose an interval that didn't include 0, but kind of symmetrically around 1, and it's differentiable on this interval as well. You can find f prime of x is 1 over x, g of prime of x is equal to 1, which is not equal to 0, so we can apply L'Hopital's rule to say the natural limit as x approaches 1 of natural log of x over x minus 1 is equal to the limit plugging in 1 over x divided by 1 is just 1 over x. As x approaches 1, that's equal to 1. For problem number 4, we're going to start like the previous example here, where we're looking at the limit as x approaches 0 of x raised to the xth power, and we let y equal to whatever it was we were raising to the power of x, and we considered the natural log of y, which let us bring down the x times natural log of x, and then we looked at natural log of y as x approached 0. And we saw that natural log of y approaches 0 as x approaches 0. And so when we considered e to the x, then y is equal to e natural log of y. Here we said natural log of y approaches 0. So this is e to the 0, which is equal to 1. So we're going to start similarly for this example number 4. Since we have something raised to the x, we're going to let y equal whatever it is we have raised to the x. So natural log of y will bring down the x, and then we have natural log of 1 over 1 plus x. Looking at this, when we look at the limit as x approaches infinity, we have an indeterminate form, because here this goes to 0, we have a natural log of 1, which is 0 times infinity. So this indeterminate form, we're going to use L'Hopital's rule, and I should say that well, here we have natural log of 1 over 1 plus x divided by 1 over x. So this is how I kind of made this in my form of f of x over g of x. I am going to use this fact here from an exercise in chapter 6. So if you haven't done this exercise for now, I'm just going to ask you to take my word for it. So the limit as x approaches infinity of natural log of 1 plus 1 over x divided by 1 over x is equal to the limit as x approaches 0 of natural log of 1 plus x over x. So I use this blue formula here to substitute in for here. So when I look at the limit as x approaches infinity of this, I'm going to convert that to the limit as x approaches 0 of natural log of 1 plus x over x. And now again, I have the indeterminate form. When I plug this in, I get natural log of 1, which is 0 over 0. So I use L'Hopital's rule again, and I should also just say that these two are continuous on the interval -1/2 to 1/2 and differentiable on the open interval. So then using L'Hopital's rule, the derivative on the bottom becomes 1. The derivative on the top is 1 over 1 plus x. As x approaches 0, that's equal to 1. And just to remind myself, this is equal to the limit here as x approaches infinity, which is equal to natural log, limit as x approaches infinity of natural log of y. So going back to my original problem, the limit as x approaches infinity of 1 plus 1 over x raised to the x, that's the limit as x approaches infinity of y, because this is how I chose my value of y, which is equal to the limit as x approaches infinity of e to the natural log of y. And here I have the limit as of natural log of y as x approaches infinity is equal to 1. So this is going to become the limit as for e to the 1, which is just equal to e, and that is my final answer. To review what we've discussed the indeterminate form, which comes when you have the limit of a quotient, limit as x approaches c of f of x divided by g of x, where both the denominator and numerator approach 0 as x approaches c. So you have some sort of limit looking like 0 over 0, and that is an indeterminate form, and that you can't really determine anything once you have 0 over 0. You don't even know if the limit exists. It may not. So what you have to do is look at the functions f of x and g of x individually. You have to consider it case by case. You can use L'Hopital's rule to help you with that. Before we looked at L'Hopital's rule, we did look at the Cauchy mean value theorem, which is this equation here. So if f and g are continuous on the closed interval and differentiable on the open interval, then there exists at least one point c in the interval such that this condition holds here. And this is a generalization of the mean value theorem. So if you plug in g of x equals to x into the Cauchy mean value theorem, you will get the mean value theorem. We went on to look at L'Hopital's rule, and we said that if we have f and g continuous on the closed interval, differentiable on the open interval, and c is in the interval, and f of c and g of c is equal to 0. So we have this indeterminate form as the limit of the quotient approaches 0. Suppose that g of x is not equal to 0 for some deleted neighborhood of c. Then we can look at the limit as x approaches c of f prime of x divided by g prime of x. If that limit exists L, it is equal to the limit of f of x over g of x. And we have this quick example here, which we went through in the video. We also looked at L'Hopital's rule at infinity, which said if f and g are differentiable on the interval a to infinity, suppose that the limit as x approaches infinity of f of x and the limit as x approaches infinity of g of x equals infinity, and g prime of x is not equal to 0, then the limit of f prime of x divided by g of x is equal to L, then that will equal to the limit of f of x over g of x is equal to L. And here was another quick example that we did in the video. For review, I have 3 problems, although this problem has part 1, 2, and 3. But I have 3 problems for you to try, so pause the video, give them a try, and then on the next slide I'll have solutions for you. This is solution to problem number 1, part 1, problem number 1, part 2, problem number 1, part 3. And I should mention, each time you use L'Hopital, you should go and verify that the conditions for L'Hopital are satisfied. I only did that at the first use of L'Hopital. And these are the solutions for number 2 and 3. That's it for this video. Thank you for watching.